months to 60 months. And then we talk about panels being balanced and unbalanced. When you have no missing observations, which means you have observed all the entities for all the periods. There is no missing data, then we say the panel is balanced. And sometimes you may not observe all the households or entities for all the periods. So you can be missing, you can observe one farm or one school for 3 years while the rest have 5 years. So that would give us what we define as an unbalanced panel. And so we can have what we call a micro unbalanced panel or a macro balanced panel. It's just nomenclature that we use here. The time periods do not really have to follow any particular sequence, that between the two time periods or the time periods, it must be exactly 1 year, 2 years, 3 years. No, it could also be defined where, because for some reasons, you may not, out of your control, you may not visit, observe the entities in some kind of systematic sequence, but for as long as you have time periods defined, so some may be equal or unequally sequenced panels, spaced panels. We've observed this, I think, with with particularly data which is collected by institutional levels. They may have budget issues, and then instead of going every 2 years, this time they can extend for another year, depending on those things. Now, panels, we can also go, rather than observing individual units or entities, you can go ahead and observe groups. Group depending on your definition of that group. So if it is not a person, if it is not a farm where which can stand alone as a unit, but rather for your research question or whatever you're raising, you rather observe groups. So some people call them cohorts. Then we talk about, you'll see it defined as a pseudo panel. And for instance, you are not going to be talking about, you'll say, I'm observing females over time. Now, this is a group, and the females, you may have so many other characteristics that may define this, which you may be interested in. Those below this age, or those who are working, or those who are married, depending on what you observe. So, but the entity here would be females as a cohort or a group. Okay, very briefly, why panel data? Again, to repeat this, we are most importantly being unique between entities or farms or whatever. Panel data is usually helps or aids in us observing what we define as individual heterogeneity. We may all be students, we may all be farmers, and we may all be farmers dealing in beans or soya beans. Now, if you went for a cross-sectional analysis, you can only tell or observe at that point. You don't have the time for you to observe the two farmers on those characteristics that may make them different, but you don't have that particular time. So which can only be observed or explained along longitudinal guidance or observation. So these are things, heterogeneity here we're talking about, those characteristics, those unique issues about an entity or a farm. But for some reason, we don't have data on those characteristics, so we cannot model them. But actually may influence your outcome variable for the people or things you're observing. So panel data allows us to have that lens, the possibility of you understanding why one entity is different from the other, for those because of unique issues, which you cannot, even if you asked them, they might not tell you themselves. But because of that repetitive observation, you may likely make some conclusion around that. So that's what we are referring to as the individual heterogeneity. Panel data has proven very helpful in analyzing issues over time, policies, interventions. When you're making recommendations based on panel data, you are possibly carrying stronger evidence, because you have observed these households, you have observed this farmer repetitively over time for the issues you're asking them. You're most likely going to help provide a better analysis and evaluate if the intervention is much better or not. Number 3 is about estimation gains. This is in the analysis section of it. What does it improve? What does it bring? Yes, you have more informative data now that you are looking at time and cross-sectional characteristics at the same time over the same individuals or entities. We are less likely to face collinearity among variables. Collinearity, as you remember, comes from two things. When it means your independent variables, none of your independent variables can be a constant. Otherwise, you'll have what we say called collinearity. Because for cross-sectional issues, for instance, somebody might tell you 50, and that is it. You move to another next individual would say 50. So your variable which you are scoring 50, 50, 50, it is potentially possible that that variable might score a constant across all the cross sections. And if that happens, depending on what you are asking, then you are likely to run into collinearity issues, which means it does not change. It ceases to be a variable anyway for that particular cause. But the panel data would help you now, because you are repetitively over time periods that you are doing, that variability may now come up when you repetitively observe an entity. More degrees of freedom, the higher the sample size, like we saw, n times t, you are talking of more degrees of freedom, and more degrees of freedom for your estimation and modeling. We are talking of you having better or efficient estimators, statistically, no. Allows the study of dynamics of adjustment. Now, one thing I didn't mention the last time is that the panels can also be analyzed on what we define as dynamics. So even we actually have what we call dynamic panel models. Particularly, we are talking about the potential of you predicting your independent variable or outcome variable based on information on the same variables, but from the previous period or the past. So example we always use here is, for instance, this month's bill for your water or electricity, among other issues, is most likely depending on last month's consumption or bill. And if that element comes up for theoretical justification, then we are talking of dynamic analysis. Okay. Panel data, the unique thing that is different from the other types of data sets we talked about is what is variations. Variations which we are observed because of the observations we make. And this is the additional unique thing that makes panel data different from the others. You are bringing variations in your analysis, which makes it more richer. So there are three kind of variables so to say by category. There are variables or regressors in your model, which we call varying regressors. So they have both a time and a cross-sectional variation or dimension, I and T. It is different between or among individuals, and it also changes over time for the same individual. That's what we mean by varying regressors. Time invariant is when a variable is where you observe a variable and it is different between from person to person or from over it is different, yes, varying between or changes between people and entities that you are observing, but does not change over time for whatever variable you are looking at. Now, these examples, of course, we use them, but they are not the perfect examples because uh, today these things are all changing. Gender changes, race changes, people always, changing, but most likely, in conventional studies, we are talking about things that are most likely not to change, at least during the variant. Now, individual invariant, where some things change between or among individuals, which are entities, over time. And that is those are things that you call individual invariant regressors. And so variations for in analysis we report overall, this is for the overall sample that we are looking at across both individual cross-sectional and time variations. In fact, time series and cross-sectional analysis, for whatever we're always doing, we are only reporting overall variation. For you're assuming that this cross-sectional units you're observing, it is everything. They may be unique, but there's constant validity across them. Now, uniquely, we can also report analysis between the variation between individuals holding time constant. Do we want to observe income of what may bring variations of income of a person to another person? And then finally, within variation, you can also report uh, hold cross-sectional units constant and then consider a single entity, and then you observe or report how the behavior of whatever you are reporting over time for a single individual as we move. Okay, so again, these are the models commonly we estimated, why each with a justification why you are possibly supposed to do that. And I just want to finish this, then we can go to start and try to demonstrate these things. Now, for general specification or analysis, I want to call this your conceptual framework is this equation. Your claim is that y, which is your outcome variable, is explained by some independent variables, and then the error term. And then this is a constant estimation if that particular case it is. Now, uniquely here is CI. CI, which we are calling unobserved effects, the unobserved heterogeneity that could exist between or among entities and have a influence your outcome variable y. The only challenge, like I mentioned, is we do not have data on CI, on these unobserved effects, and therefore we cannot explicitly model them. But we know that these effects may influence your outcome variable, and therefore your study, and that's what makes it an issue. So all these models we are going to run through rotate around how do we manage CI, and that is what exists under panel data. How even if they are commercial banks, what are those unique issues that what we don't have data on to model, but make these commercial banks different? You may ask managers and employees at those banks, they will tell you up to some level some things, but you'll go around and find out, but what then if you are the same people what makes this branch different from the others? They may not tell you themselves, but some characteristics, unobserved issues may be the reason, and that's what we want to control and manage. So these models, each of them attempts to show how do you handle this if it exists, or usually because it exists and influences. The first case is what we call the pooled OLS. OLS is ordinary least squares. We are observing between and within a variation to estimate the parameters. Uh, Parameters are constant, meaning it's just like cross-sectional assumption. When you are running a cross-sectional analysis, this assumption is what we are running on. That estimated parameters are constant, and so between even the intercept is the same. So between among the entities, you are assuming a lot of uh, and little variation, because you are meaning that the parameter for between among parts of individual A, individual B, and individual C are the same. So, but still, number of observation is uh, cross-sectional and the time dimension, which is NT. Now, for pooled OLS, you are making one big claim that while C may exist, you just close your eyes and say, for my analysis, it doesn't matter. And so you just drop it off, and then you just estimate your analysis without a C. Of course, you need very convincing and the theoretical justification is why you are just dropping C, or why you think these unobserved effects do not matter for your analysis. All papers report this, but it is very rarely reported because you are, as collapsing the data characteristics into a cross-sectional analysis. And that's why arguments really have to be very strong for you to present panel data model or a pooled OLS, because you just come out and drop C, and then you go ahead and analyze whatever justification you're going to make. So when we are running this is what we'll be assuming, the pooled OLS. This does not matter or does not influence my variable. Even if it exists for me, it does not matter, but it is usually more of a theoretical justification. Then you go ahead and do that. For second one is what we call a fast difference estimator. Again, I start with my general specification or my general conceptual framework for a panel data analysis, where C is an issue of concern. Now, for a fast difference, you take changes, or what we call differences, one period changes for each individual. Which means we are not looking at absolute values that you are reporting. You rather, the one period change. This is the same variable, but only across 2 time periods. So the change is, today and yesterday, you just get a value for today, and then minus value for yesterday, and then you'll get that change operation that we are looking for. Now, most importantly, why do we do that? There are 2 reasons. One, for potential omitted variable bias. That this specification you have made, that this conceptual framework you are giving us, we understand there is potential for you to have omitted some variables, either because of theoretical reasons or explanations, or sometimes unaware that you have omitted some variables in your conceptual framework or in this specification. So should that happen, then you are bringing all the variables together to the same level, so that when you difference, so that that bias does not go away, but it is minimized. But importantly, for estimation reasons, people who have worked with the time series data, because your panel data has a time dimension. So your variables can be influenced because of time effects. What do I mean here? In your estimation or in analysis, the assumption is of linearity, but some variables may move up and down depending on time effects. Theories like income, population, prices, etc. are not, their variations are not linear form. We couldn't observe them in a linear form over time. They could have what we call seasonality, where in some months prices go up and then keep coming down and going up and coming down. So there is that volatility. That volatility may influence the behavior of that particular variable. There are some things we also call trends, and trends have influenced sometimes over bulge or shrink a variable depending on what you are referring to. So to correct for those things, for those seasonality, for those cyclical movements, we difference. With differencing means you are removing the extremes and looking for the average value for that particular variable. So the same, but doing that then removes the CI. CI is, as you see here, it doesn't have a time dimension. So it will be a constant. When you difference a constant, it is a zero. Or when you take changes of a constant, for those with your mathematics, you know, it, the change from a constant is zero, becomes zero. And therefore you'll have that this particular equation change in y plus your alpha, a constant, uh, for these then changes in the explanatory variables and then the error term. Time invariant variables are also dropped. Those variables which do not change over time, they will also be dropped because the changes in a constant, like I've mentioned, also become zero. The third one is the fixed effects, which we didn't want to talk about the last time or demonstrate the last time because of its behavior, and it's one of the most pronounced estimates as for in panel data analysis. Now, you are observing within variation. That's the biggest issue about this. Within the same individual over time, what is causing that variation in your outcome variable? And this is one unique reporting we make because of panel data. Now, when you go for cross-sectional, it is hard to observe this same individual or household over time because you don't have that time dimension. But even if it was savings, for instance, even if it was income, even if it was any other issue you're observing for profitability for instance, a bank, it is impossible, it is very hard to observe that variation for that particular time because you're just going at that time and they report as at that time and that is it. But the panel data will give you a chance to observe that variation within the same farm, within the same individual households over time. The only difference here is to manage CI is that we use what we call the mean variables. The mean variables, doesn't change anything. You get your specification or your conceptual model. Rather than using YT in levels, if somebody records to you, my earnings is 10 million, 4 million over time. Rather than using those values in levels, we demean them. Demeaning means you get a value, which in the raw form, the way it is reported, you have the average of that value, and then you remove it from the original value. So the Y which you have on the left-hand side is not a YT, but it will be a YT, but we call it the mean. The mean because they have removed it. It is a difference between its value and its mean. Same thing to all explanatory variables and also to the corresponding error term. Now, by doing that, this is the time averages we are getting them. So in other words, get this equation, the original one, minus this average equation, which are talking about this. So yit minus yi is this left-hand side. Alpha and alpha will go. So it is a and constant estimator, but we can, of course, give a restriction and say, no, I still want a constant. Now, beta out, we shall have xit, which is this minus its mean, and that's why we have this character, and then this. We do not lose ci per se. We are only trying to manage it, meaning I can come back and retrieve ci and report it after I've estimated my fixed effects, and we'll show that. So this is number of observations main, and this is what I'm referring to. After the fixed effects estimation, you can come back and then even report the individual, those unobserved effects based on that sample that you have used for estimation. Most importantly, therefore, the big requirement though is that your model needs to exercise or behave on the principle of exogeneity. Otherwise, endogeneity issues will make your model collapse. And then the final one is the random effects model, which is usually a trade-off. Do I run a fixed effects or random effects? The difference here is that individual specific effects CI are assumed to be random, and therefore they are not correlated with the independent variables. For a fixed effect, I forgot to mention, the reason you are demeaning these things is that there is a potential relationship between CI and your independent variables. And if that happens, then your assumptions of estimation collapse. If you remember the assumptions before, we said there should not be that relationship or correlation between independent variables and the error term or that unobserved specific effect. So for random effects model, it says assumed to be random. Therefore, CI has nothing to do with independent variables. It is a big assumption. Therefore, carries these unobserved effects and they become part of the error term. Again, another big effect that you are bringing here, or assumption that you are making here. Potentially, therefore, this error term, the new error term, which is a composite of now the original one, plus these things you are putting here, most likely to be what we serial correlated. We are meaning when we talk about serial correlation, we are talking about an error term in period 1 being related to an error term in period 2, and so on. And if that happens, we say, well, your model is serial correlated, and you are likely to produce unbiased estimates for estimation, and that's what they don't want to happen. So all this, what will be happening, it is one way of managing this with the data assumption, but we'll go ahead and demonstrate what brings that difference. However, statistically, it means based on your data, you can also decide, it can inform you. Somebody is writing here, I don't know. You can also choose based on your data to Reverend Canon Duncan Mugunia, I think, I don't know. So you can decide to do that, and based on your data, run a test to find out if your estimates based on fixed effects or random effects, to choose between which one. And the hypothesis here is that no correlation between individual effects and independent variables. In this case, fixed effects and random effects coefficients are not significantly different from each other, meaning the null hypothesis is for RE, which says there is no relationship between CI and independent variables. And the alternative is that the null is not true. But most importantly, the difference between estimates based on coefficients based on RE and FE and their convariances are the same. So this is equal to 0, this bracket, versus this bracket not equal to 0 if they are indifferent. And this is the conclusion we make based on this test, or whatever it tells you. If the test is significant, then we reject the null. And if the test is not significant, then we fail to reject the null. And I hope that puts us back to our original thinking, revision. So now when I get back to start and run, now we know what we'll be doing. Okay. Dr. Kochi, unless there is a question, I'm going to go back to, I'm going to stop this and then we go to starter. And then I will.
Yes.
Then we shall.
Yes, if there's any question.
Yes.
I think we just proceed. We proceed, please.
Okay. That's all right. I'm trying to find my folder here. Just a few seconds, please. Okay, I'll go back to this. I'll share. And so I'm launching my starter, or you can launch your SPSS or whatever you use for analysis. You have your data sets existing somewhere. So step number 1 is to find or locate my file or data, and there's a simple putting of the word. That's what. So we start to recognize a spreadsheets, and all have several types of words. If you are in X, you have to, I told you last time, you have to save a file or data as delimited or CSV, and that's I will bring it. So which file to import, I'll browse. It is on my desktop, and this is where it is, and the file I want to work with. Anything else? No, I'll say open. It just shows me if this is a preview, if this is what I'm interested in bringing, and if I'm comfortable with the file by what it is, you would have entered this and seen it. Click OK. If I click OK, my variables in my data set is here. I go ahead now, start with the analysis with the preliminary. So again, this is you execute it, go, our results will black green, and my variables are. Like I mentioned before, I can browse and see, look at the data which I've brought, okay, and run. So it's just a spreadsheet, and find out. So what is the panel about this? We are talking of ID, or these are entities. And these are the ones we are observing. And these are the ones observing. I have entity 1, 2, 3, 4. I mean, entity 1 observed for this time period. I have entity 2 also observed for the same time periods. I have entity 3 observed for this time periods, and then so on. And the next one about it. This is the data which variables which I just need to attach some meaning so members can understand. You could have done this in Excel, but you can also little sensible. So I will again, just for illustration, use these take 3 minutes to do this. I will label, it is a variable called ID. I don't know what it means, so put in full quotes, and this means individual or person. And once that individual, the person, and then you close the quotes. When I enter or execute now, it's just a label, the meaning of this variable, or how is it measured. So I will recall this and also label another variable, which is t. And this variable, it is time, and time could be weeks or whatever. I think for this particular time in weeks, was data in weeks for this course. And we have another variable which is called label variable LOH, and the LOH is starting for log of wages for the workers and sample. We also label another variable to just attach meaning to this. There is EXP, which means years of full-time experience. There is another variable which is standing label variable WKS, which stands for number of weeks worked. And there is another variable female. What does it stand for? It is a dummy variable. It is a dummy variable for gender is equal to 1 if the individual you are observing, if the individual is female, and therefore 0 if it is 1. It's just a dimension variable. There is another variable, EDCU, and this is standing for years of for individuals. We have OCC, which is standing for occupation, and the OC is just another dummy variable. So what they call the blue collar occupation. Blue. Okay, and then finally, having a variable EXP squared, which stands for square of experience. square of experience, and that's what they stand for. You could also interact experience and the gender experience and education, like we do for interaction variables, and depending on what is suiting you. So now at least I have meaning of what these variables are, what we are going to work with. It should have been done in Excel or when you are entering your data, but we also brought here for just demonstration. So you may see every command or activity executed, it goes here. Of course, you'd also come here, you go to data, and then follow this menu to label those things, or the variable manager. I think this is where I would go, and then you label things for, come here, export what it is, finish, just like you do, for instance, in SPSS, and then you do that. Okay, now that I have my data set open and I understand what this is, the first step, of course, is to, like you mentioned, folks, first, if you just start running and analyzing now, by default, you will be running a cross-section analysis. That's what Stata is. If it is time series properties you're interested in, you first have to alert Stata that now I'm going to be running time series properties. So same scenario. If you want to panel data, then before I start running all the estimations we just walked through, I have to alert Stata that I want to run panel data estimations and the characteristics for this case. So the first thing is to sort by the identifiers. Identifiers are the dimensions, the individual, the cross-sectional versus the time. I'm just going to sort by ID. Usually it is by ID, then by time. That's why I have the N and the T. Just be sure the data set is sorted according to those two dimensions. Then the next issue is to alert to set, to alert Stata that I want to run time series, panel data characteristics. And it is an XT, it is a CSL language, XT set. That is, if I wanted the time series, I would say TS set, but for panel data, it is XT set. I want to set by ID and the time, and the result here, it tells you what kind of panel you are running. It is telling me strongly balanced, meaning I have no observations for all cross sections. The missing observation is that for all cross sections that were made. And the time variable is 1 to 7, so I have 7 periods for each of the cross sections that we have to make. So just like any data set, once you load it here, first step is to describe, to inspect, to see the data you're working with, look for outliers, look for values that may feel relatable with your data that you are doing. So every time we are going to be running panel data estimation, you just have to start with XT. Every command execution you make, it is an XT, then you put whatever you want to do. First, I want to describe just to see, because it could have been given this data, you want to understand what it is for these variables, what they are. IDs, which means I have how many cross-sectional or entities or individuals do I have from number 1, and the last individual is 595, meaning I have 595 workers for this particular data set. Time dimension, it is from 1 to 7, meaning the periods are 7 for that particular observation. This, it just tries to display the frequency for these dimensions that you're having for time I, and then frequency for the individuals you're having. Now, if I had missing issues, if the data was missing in some, it would have displayed this and say, while the total is 595 for the data, which would be fully having, would be maybe if I had 5 missing observations, anywhere I would have 590 just for a display. I also want to characteristics about these variables themselves, summary statistics, XT sum, or for summarize, and just list all the variables which you want to play and understand their summary statistics, what they are, and which gives us this different table unless compared to the other one which brings for the whole sample. Now, just a caution here, of course, you are working with your data set. The first two variables are not variables per se. They are just individuals and time observations. So the first two variables, I don't expect you to present them in a paper for publication because they don't make sense. It's just an individual, so you can't have a maximum individual and a minimum individual. So that's why. But I just brought it here so that people know, understand what things you should be. So you should know what you report on the character summary statistics. So I have wage, which makes sense, the log of wages at least. I need to know its maximum, I need to know the minimum. Of course, if you want to know the real wage here, mathematically you get an exponential of this, it will give you the exact wage that when the logs are off. Change this from logs to the real values. So overall, the average log of wages is 6.67. Standard deviation or variation across the whole sample is 0.46. The minimum value for the whole sample is 4.6, and the maximum is 8.537. That's what we mean by the overall summary statistic here. The between, meaning between individual 1 and 2, this is, there is nothing with mean because that will be now irrelevant. The variation here is what we are interested in, between and within. And what do I mean by within and between for a recap? Now, between is we are looking at individual 1 and individual 2 or any other comparison here. What is the variation of log in wages between individual 1 and individual 2, for instance? And that's the variation we are looking or interested in. You could also see this one keeps changing for between individual 1 and 2. Now, for within, you are holding ID constant and you are looking at, for instance, the first individual. How does the log of wages vary across the 7 time periods, the 7 weeks there, or periods that you are looking at? So this is the within variation, and then between 1 and 2 and 3, we are talking of between the variation, while same individual over time, we are reporting the within and between issues that we are talking for. So for this one, that's what it means. We are talking of variation between, and then this is individuals. So what we can only report here is there is higher variation of log of wages between individuals that compared to within an individual. So meaning wages vary more between individuals compared to a same person over time. And that's what it stands for here. So between the maximum individual minimum is 5.3, while the maximum is 7.8. Now within the same individual, the maximum log of wage is 4.7 and the maximum is 8.6 to 1. So the same explanation holds for this. EXP is experience, years of full-time experience. The average experience for overall sample is 19.8, and with a variation of about 10. So the overall, the lowest years of full-time experience is 1, some have been for 1 week, while others have the maximum of worked for 51 weeks for that duration. Between individuals, the minimum is 4 weeks of work, while maximum is 48. Within the individual, it is 2. This is the average experience for within an individual. On average, we can say within analysis, an individual on average has worked for at least 2 weeks or 2 years, whatever time periods. But the variation, the maximum, the minimum is 16 and the maximum is 22 weeks, depending on this sample data. So that's how you go talking about these summary statistics, which is a little unique or different from the cross-sectional summary statistics we have. Observations for overall, it is n times t, which is 4165. If you're a cross-sectional analysis only, we're talking of 595. If you're a time series only, it would be 7 as the sample units. So 595 times 7 should give us the 4165, which, if you remember, we talked of more observational data as one of the justifications for panel data analysis. Okay. I think it's time now to go to the estimations themselves. We had 4 models. The first one is a pooled OLS, like I mentioned. The pooled OLS, you are talking of, you are saying that the unobserved heterogeneity does not matter for your estimation or for your conceptualization. That while it might exist for my analysis, is not an issue here. So I'll go ahead and just estimate it like an ordinary, even if ordinary OLS, and that's where it comes from. OLS, you have just increased the sample size, but the assumptions of cross-sectional are actually what you are riding on. Even if you don't put reg xt on this, it just implies you have the cross-sectional assumption. So I'll put reg for regression. I want to regress. In starter, the first variable you start with must be your independent variable. And my independent variable here, which I'm observing, is log of wages. Once that is done, then you can populate all the other independent variables in your model, and then you go ahead and analyze. So that's where things come from. So, so my independent variables, I have experience, I have weeks, number of weeks worked. I want to see if there is variation or gender matters between males and females. I want to see years of education, if they actually also explain earnings. I want to see variation between the 2 groups, those who are employed in what we call blue-collar jobs or occupation versus those in other occupations. And then because there is a potential theoretical relationship between wages and experience, a quadratic relationship that the wages and experience may have a quadratic relationship where wages will first increase with experience and then afterwards earnings will drop with more as experience increases, and that's why a square. We could also interact variables here and add them, but this is where I'll go for now. And shoot, and this is our output. Sort of gives you your ANOVA, gives you your observations or significance for the overall model, and then you will get your coefficients with all. I don't know if I have to repeat this because we did the other time the meanings of all these numbers here. Maybe if somebody has a question, could ask if they need any question on this. Otherwise, interpretation here is exactly the same way we interpret cross-sectional results after you've run them. And so experience, for instance, remember this is a log of wage and the experience is not in logs. So other factors constant, an increase in the year of full-time experience by 1 year is associated with an increase in log of wages by 0.0 wages by 0.04%. Because experience is in levels or units, while wages is in logs. So the unit here influences the dependent variable in percentage terms. That's what I can collapse it to this. It could have been wage here, which has no log, and experience would have a log. So the interpretation would reverse. It would mean a percentage increase in experience, percentage increase in experience would increase now wage earnings by $0.04 or shillings or whatever that would be the case. I observe T is higher than 1.96, which is the 95% confidence. And we remember we get T, just divide your coefficient by the standard error or the standard deviation, should give us this 18.72. T above 2 is the coefficient is significant. With a p-value less than 1%, this is even significant at 1% because 0.00. So we could go ahead and interpret this because it is significant and it makes sense for this case, as would be. And okay. And so it would be the case for that. Weeks worked would be the same. Dummy variable, the language changes here, which means you are comparing males relative to, females relative to males. So what does the 0.4 minus 0.4437 here mean? It implies that relative to males, that's the base category, log of wages for earnings are lower for females by this percentage because it is a log and wage. For wages, for earnings or wage earnings for female workers are lower are lower by this percentage because error is in percentages. So the same thing would do mention to this. Now, what does the experience here mean? It is square. When we squared it, I mentioned that is probable potential quadratic relationship between wages and so we are saying experience initially increases. When you are talking of a potential quadratic equation, it is a curve. As experience increases, earnings will increase, reach a maximum, and over time, actually earnings will start reducing as experience increases. And you must have a theoretical justification if you think in your conceptualization that is true. So what would this mean? That, for instance, if you are talking about the 7 years or the 25 years of work, would give us a positive relationship between experience and wage earnings. But after 25 years, earnings will start dropping as experience increases. And you'll have theoretical foundations for that. One, you may have just retired for whatever reason, and therefore your experience will not reduce. Your experience will actually keep increasing. But if you have retired, then earnings will start going down. And that's one justification you may have. Two, people right now are having experience, could be because of unexplainable factors like COVID, which you're having now. Some people have been have lost jobs, are now home, or have reduced incomes. They have taken lower pay because of COVID, but that as their experience has not reduced. So with more experience, earnings can go down depending on what you are earning or taking. So and then finally, the constant. The constant is the value of the average value of your dependent variable when all these independent variables are zero. So it is the constant is the value or the average value of your dependent variable when all these are zero. And that's what constant represents here. Some models constants matter. Some models constants may not matter because it may not even make sense. That's what is supposed to be. Again, look at the coefficient, look at the significance, and then you interpret accordingly for your issue. So that is how we analyze pooled OLS. We close our eyes and say it doesn't matter. That is it. So we'll just analyze it and say those observed effects do not matter. And most likely, this is how cross-sectional assumptions may make. That's why your paper may gain strength if you go panel data, because somebody may most likely think, while you are saying the bank A and bank B and proposing all those interventions, you may give the same banks the same interventions, but the outcomes will be different. For your target issue just because of unobserved heterogeneity. The next model is what we call the fast difference estimator, and we talked about why we difference this. We regress, taking changes of all variables. Like I said, you will say D of LOH, again start with the independent variable, then you'll have D of experience. You are differencing each of these, just a short command for this. You will say difference of the next variable, which is W, number of weeks worked, and so on until you finish them. But I'll just save, you can also in a short way, just put a D dot, and then inside you put all the variables that you are looking at. I'll have LOH, experience, weeks worked, female, this matters, and then all this. I close the bracket. And just because.
Yes, Bernard.
Yes, please.
Thank you. I don't know whether there are comments arising from so far what we have done. I've just seen one of the comments from Dr. Charles, but I know there could be other comments.
I hope I can't get in there to see.
The comment is saying that which could be the most important areas in terms of publication. For the purpose of publication, could you suggest the most important parts needed? Otherwise, thanks for the support. But I also believe that there could be especially members who never attended last week. Right. In case there's anything before we proceed.
Right. So not very clear about that question. When we talk about most important areas for publication, the things you should talk about, or which model to run?
Dr. Charles, maybe you could do.
Yeah, you could ask.
Yes. I think we proceed. It's not.
Okay.
Yeah, just proceed.
So fixed estimator, and these are the reserving particular nets. If I'm here itself, the education also omitted because of coloniality. Again, because of, if I'm to take us to the data itself, why is it omitting female? because it's between non-constants, feeling more of a constant in this particular case. And then we also had education. Here is education. Within an individual for this particular data set, it could be a different story for another data set, but for this individual, education for a person seems to be constant over the same period. When I come to the person too, education is not changing, it is the same. And potential is why it is omitting it. If we see in 17, 11, that variation within, then that's potentially why it is dropping it. And that's what differencing does, because 9 minus 9 is 0. You come here, 11 minus 11 is 0. That's why it is potentially omitting it. But that said, so what does this mean? I'm seeing a positive relationship between experience, that one period change in experience is associated with an increase in log of wages by 11%, because again, log wages is in logs. What means here means one period change in number of weeks worked is associated with or reduces the log of wages by this particular percentage. Again, we go with the significant issues. I wouldn't interpret in its second variable because it is not significant, and as well as this. So I would only talk about experience here, and then experience squared, which seems to also matter for this particular case. And the third one, which is the most important between mostly commonly run most commonly run model estimation is panel data is either fixed effects for what we explained. So it is xt rate, xt rate, and then you'll populate your independent variable first, and then you add all the dependent variables that you have for your estimation, and then you'll just add an option FE, which means fixed effects, and Stata recognizes this case. Now you can observe the outcome here. If you observe this output and the end of this output, you can almost tell the difference even from the ANOVA process. Now, within regression, this is the most important, but two, we are talking about the analysis here is within largely for reporting. And then two, the most important issue here is to know that the unobserved effects, the CI, are potentially correlated with the independent variables, and that's how we have to manage them. We have to demean the sample, and everything does not change. The number of groups, which is number of individuals, is 595. So the meaning does not reduce the sample size, the meaning which is fixed effects. We have 3 R-squared values, and the first one is within, and the other one is between, and then the overall. We can see these are more of relatively less importance here because the attention with fixed effects is within. So in reporting these results, your attention should be within. But what does between mean for this particular case? That the variation in your independent variables for this model, the total variation of log wage because of a variation of in all independent variables between individuals is 2%. That's what would mean by the R-squared. But the 6.5 R square here is variation in log of wage because of all these independent variables within an individual, which means you're observing between period 1 and period 7 for a person is explaining 65% for that particular outcome. Again, this is the significance of, this is the number of periods, this is the significance of your model. Significance, as we know, of a model based on this statistic, it means we are talking of how jointly significant your independent variables are in explaining, in predicting the dependent variable. So it is a higher, and the higher the F value, the better. And with a probability value, its probability value, of course, is telling us the significance of this F value. I just have to put some kind of caution here for people usually always, loosely using words. Significance of the model, because this is your conceptual framework. Significance of the model does not assure you the how right or wrong your specification is, or how right or wrong your conceptual framework is. I think that's a better word. Meaning that you can still have a significant model for a wrongly conceptualized model or theorized model. So please, this is only as per this estimate that you have made, so that we can now rely on your model to make inferences for the population. But again, the theory behind all these things goes back to your conceptualization and theorizing. So people sometimes think the significance of the model makes your conceptual framework true or very believable. No, it is only for the specification that you have made based on this sample. We can now rely on your sample results to make conclusions about the population. That's what the model significance does. Whether your conceptualization is wrong or right, we don't know. But it is only telling us that for the sample results you have given us, it is significant, meaning we can use it to make inferences about the population. Now, correlation between the independent variables, the error term and the independent variables, it tells you here, because I told you fixed effects, there is a potential relationship between independent variables and the error term and the unobserved effects, which could mention to this. Now, the interpretation is exactly the same way we have interpreted the other coefficients. Again, look for significance values. They are the ones you interpret. So I would interpret experience. I would interpret experience squared. This is not significant. These were omitted because of the same reason as I showed you. When there is no variation, that variable is dropped, because the mean minus a constant of a mean is the same value, which would collapse when you are demeaning, and that's why probably mention this. The important statistic you have to pay attention here is this rho. Rho is the fraction of the unobserved effects, the CI, fraction of CI in explaining your dependent variable, which is log of wage. Meaning the closer and higher it is to 1, like this particular one have 0.97, the better. Meaning you are recognizing that there could be some unobserved effects among individuals that could influence variation in wages for this particular claim or model, and that's why we want it positive and higher or closer to 1. It is a variation. It is an error term, that is special error term, where we cannot model or make it independently an independent term variable, but we know it can influence your outcome variable. So if the value was very close to 0, then we would say for this particular sample or data set, there or whatever you have been observing, there are no heterogeneous, unobserved heterogeneous effects that may cause variation in this. In fact, the C becomes irrelevant in explaining that case. So if it is positive, and it has to be positive, of course, because it is a squared sum anyway, should be positive and closer to 1 for it to make a justification and therefore explain that it is a part of the variation in this case. These are just the other error terms, the official ones. But the most important one is this row. So the closer it is to 1, then you are recognizing that it is impact on your outcome variable is exist. If it is very close to 0.000, then would say it does less, and people would say, okay, fine. So, but for this case, we recognize that it actually matters for this case. And finally, which I want to compare with this is just estimation. But in this case, I am putting RE for random effects to just get a difference. Now, what's the difference here? The difference is this correlation. The unobserved effect CI, which is now part of the UI, has no relationship. This is an assumption, has no relationship between itself and the independent variables X. The rest of this is the same story. In the F, this is the chi-square is just now moment distribution, which means, but it's also testing significance here, which means your model is significant overall. Jointly, how all independent variables influence your outcome variable here, it means it's significant given the statistic. The interpretation here, you talk about within, which means within the individual over time. Between, this is the R squared, between individual one and the two or the other across the sample. And overall, our independent variables explain about 23% variation in log of wages. Again, the interpretation here is the same, like I mentioned before, and the p-value here, because now it's a Z distribution. Again, I find the experience significant. There is a gender for females. There is it's only number of weeks worked, which is out of range, which is not significant. Again, the last issue you should concentrate on interpreting is the row, which still means that it represents the fraction of the CI in explaining variation in your log wage. So 0.7 is still relatively high value, meaning that unobserved heterogeneity or effects among individuals do have a strong explanation for variation in their wages. We may not observe them, but there are some characteristics about those individuals in this sample and which have a big bearing on their earnings or wages. Could be ability, could be intelligence, could be things that sometimes themselves may not even be aware of, the respondents themselves, but they bring that influence on that case. Now, the last question is, you have estimated this. The first two have their own justifications. Now, how do I choose between reporting fixed and random? I first want to mention that usually papers will run both, and then you will finally take a test, which we talked about as the Hosmer test, then decide which one should be reported on in your finding. And this is where it comes to. So we are saying two models. there is a potential relationship between unobserved and independent variables. I determine the variables, I manage it, I estimate, and then I have these findings. And then I come here, I said, no, this one assumes that the unobserved effects do not have a relationship to our independent variables. I come here, and with those assumptions, I run. Now, the issue here is between these coefficients and these coefficients. Okay, first, between this one and this one, the model itself, one, we can compare at the R squared values, particularly the within, which we want to observe, because this CI is between individuals. The within R squared, before I even go for the test, the within R squared effects and soft effects giving a better explanation or account compared to this. They are both in 60s, but relatively we choose that. Anyway, let's do this test and then we'll interpret it and then we'll go with the interpretation to see what it means. So you'll to do this, to choose between RA and FE, I'll first say you'll first run the two estimations, but start by saying quietly or store them so that it doesn't execute them, and then we'll compare afterwards. Quietly, xt reg, regress, log of wage, and all this, which we have done before, called with FE. So it does, by saying quietly, it does, you run, but it runs, but it does not display. I'll say estimates. I want to store that estimation, which I've just run, because I want to retrieve it when I want to compare. I'm calling them fixed. I will also, can see when it brings it here when you're storing them. I'll repeat the same estimation, but I'm doing RE. I'll enter. I'll also say estimates, store, and I'm calling them random. And then a test, which is the Huseman test. I will just now say Huseman, which is the command here, and then you'll bring your fixed estimates and then random estimation, which you have just run to give us that comparison. Oops. Sorry. The name, should have used the name. I called them fixed and random preservation them. Okay. All right, so what are we doing here is remember the test that we are making, that the random effects and the fixed effects are different and not different, or meaning they are the same, versus the alternative that the estimates from these two estimation models are different. Now, use a simple case for this meaning. If we had the difference, you are seeing B minus B, uppercase. If the variation, the difference here was closer to 0, meaning 0.000, meaning the difference between this one and this one is 0, such that this coefficient would be the same as this. This coefficient would be the same as this. So we would reject the null, which says there are no effects between the independent variables and observed effects. So it is significant here, meaning with this particular chi-square value, meaning the null hypothesis is that the difference in a coefficient is not systematic. So meaning there is no relationship between the unobserved effects and the independent variables. If that is the case, then we'd go for random effects. But the alternative here is, in other words, just saying no observed effects. So we are rejecting the null because it is significant here that there are no objective, no correlation between independent effects and the observed effects and the independent variables. So we are rejecting the null that the fixed effects model is not the same as the random effects model. So which one should we go for? If you are rejecting the null, it means you are favor of the fixed effects. So you estimate the fixed effect and not the random effects. If we failed to reject the null, if the p-value here was 0.7 something, which means below 10%, I mean above 10%, we would fail to reject the null, which says no, and agree that there is significant there's significant difference between the random effects model and the fixed effects model for this case. So, but again, this is a data-based conclusion. This should be done in addition to your theoretical foundations. Why you run fixed effects and random effects has to come from the theoretical specifications. If you believe that CI has a relationship with independent variables, technically you are looking at a fixed effects model because that is its assumption. If you believe theoretically that CI is not correlated with your independent variables, with your conceptual framework, then you'd run a random effects. What do you observe here? We observe that this 0.77 and then 0.097, which is even being favorable. I say the higher or the closer it is to 1, the better for that estimate. Even you could just rely on this to tell whether I should run a fixed or one. Both are positive, both are high, but it is higher for fixed compared to the random. So you are believing here that the unobserved effects CI actually have a bearing on the log of wages. And that's why we are saying go for fixed effects relative to the random effects for that conclusion. The language is always confusing, but depends on the null for any hypothesis that you're stating. Dr. Okocha, I think that is it for now.
Okay, thank you so much, Bernard. I want to really appreciate you for the elaborate explanation. And members, you can agree with me that 3 weeks of consistently being able to create value takes a lot of effort of research, and also it's a really strong, intelligent pursuit. So I think I want us to appreciate Bernard for the good work. And I also want to acknowledge all the senior colleagues who are in the platform. I think I want to begin by appreciating Professor Laura Robia, though I think maybe she had internet problems, network. I also want to appreciate Professor Janet Bagorogoza. You're welcome. I also want to appreciate Dr. Goret Cheone. You're welcome. I also want to, my appreciation goes to Dr. Jolie Kabagambe. You're welcome. I also want to appreciate Dr. Isaac Kayongo. My appreciation also goes to Dr. Ahmad Walgembe. You're welcome. Dr. Charles Kawalia, you're welcome. Dr. Wilfred Coker Saupal, you're welcome. Dr. Gideon Kruzinza, you're welcome. I think this time we have a lot of time for discussion. And if you recall last week, the session of today was on the basis that we didn't have sufficient time to continue with the discussions. And a lot of issues really came up which could not be handled within the given time. So I think today we have a lot of time, which will help us to ask questions, which also will help us to make clarifications. The other thing also I remember, I know there are comments in the chat room, but also I remember last week, Dr. Gideon was let down. Most of the senior colleagues were let down by connectivity. Dr. Gideon was trying to make a submission, but internet let him down. So I believe that as we wait for Bernard to, because I know he has been he has taken time to take us through all this, and through the presentation, there could have been questions or comments, points of emphasis, maybe which somebody, one of the senior colleagues could do. Want to add? I will be able to, let me now take this opportunity to invite all of us. But of course, above all of us know that Professor Joseph Ntai has been the brain behind this platform, and we really must all appreciate him for continuously hosting us in this platform and giving us opportunity to share knowledge and learn. And all of us agree that there's a lot of learning taking place. So at this juncture, I think let me take the opportunity to invite anybody with a comment, but also members let us join the appreciate Bernard. I think this has been really done to precision with a lot of simplicity, with a lot of accuracy, helping somebody who had never even heard about panel data to even go further to interpret and analyze panel data. Okay, let me invite members to make any comment if you have any question, if you have any addition, you're welcome. Frederick, you have any comment?
Okay, I'm seeing some questions in the chat, I think.
Yeah, you can go ahead and address those as people are composing. Yes, thank you. Please go ahead and address them.
Share this. Okay, Jose was asking how do we interpret sigma U and sigma E? Now, rho was for the unobserved effects CI. Now, panel data analysis has a timed in the cross-sectional dimension, which would go for, it started by default around an I dimension, which is U, and also a T dimension, which is in this case E. So these sigma U and E respectively correspond to the error terms for the time dimension, for the cross-sectional dimension and the sigma dimension. Again, like you always interpret the error terms, this is the variation of those other error terms on cross-sectional observations that could not be accounted for in outside your conceptual framework in simple terms. So the E is for on the time dimension. The N and the I and the T definitions that we had before. I think that's what Sylvia was saying, how the interpretation of RA and the fixed, there is no difference. Interpretation of coefficients is the same. The only difference would be for within, and that's why the debate is between. In other words, these two are the same. The issue is which one do you choose to report? If there's no significant differences, then you back up with your theoretical justification and move on. If there are significant differences between the coefficients of RE and FE, that's why you do Hussman, and then finally base your argument and the interpretation is on which one is more favorable to explain your issue. Actually, by doing that, you are just trying to strengthen your conceptual framework, which is the independent variable and its independent, the dependent variable and its independent variable. So RE and FE would say they are talking about the same thing. It's the only belief if this is, if you, the assumption of CI being related with the independent variables, that makes you choose one over the other, but they do the same job. This is just for statistical differences. Okay. Just trying to look for any other issue here.
Then there's another one from Peace to Shabe. How do you work out with mediating variables? Thank you for the hard work.
Okay. Peace, thank you for that question. Statistically, in Stata whatever, you'll still add it as an independent variable. That's where to start from. But usually it is the conceptualization where you start from, which you define for us, whether it is which it is a mediating variable. In econometrics, though, it does not stand out alone. If it is mediating, we have to tell us which variable is it mediating of the independent variables that we have specified. Meaning you'd have to re-estimate, you first have to re-estimate the variable which it is mediating before we bring now the mediated variable into your estimation. You've heard of approaches called instrumental variables, where you put in where some variable X does not have a direct relationship to the dependent variable, but comes through some other dependent variable Y. So you'll have to first re-estimate the relationship between Y and X. We get the error terms, which is all the, we get the predicted values now, the estimated values of that relationship, then bring them and add them into our equation as a second stage. So if you are familiar with approaches called instrumental variables, two-stage least squares, so that's what people do first. You estimate the variable, the variable and whatever mediates it, you will have some estimation. So now the mediated variable is not the original variable, but the mediated variable, which means you bring the predicted values and then you put them in the estimation. That's pretty much in econometrics and economics how we handle mediation issues when they emerge. Theoretically, you'll have that justification, of course. So that's how it comes. Okay.
Okay, thank you. There's another one by Dr. Charles Kawalia.
Yes.
Yes.
For purposes of, could you suggest the most important parts needed? Let me see, for both models and figures. Okay. Let me try to share this again for reference. I think for the second part, this is what we are talking about. The choice between any of these models. You must have a reason why you want to run pooled OLS or you want to run fancy difference. There must be some compelling factor behind that. And first, and then largely panel data approaches is fixed or random effects. Again, these two are the same. What makes you choose between these for publication? Actually, usually you run both and actually present both models in your table or your results, but you base your justification on which one based on this particular test. Now, certainly you don't present this whole thing in your write-up. Where needed, this has to go into your appendix. You have to extract, most important is number of observations. You tell us the R squared, this one you have to bring the 3 of them for your paper. You'll extract probability significance or probability value here. You'll tell us the variables and their coefficients use, and then these error terms which have to be reported for reference purposes, because this is where your full model for pan analysis will do. So just like we report tables or values for even cross-sectional, there are really particular things you have which you must show in your table. The other things like this one, you don't have to put it in your write-up for whatever things it is implied. Even this is an assumption. Once you say FE, somebody will know this is what you are working on. So you don't have to display each and everything. And then all these meaning. Certainly, of course, you get this table. Like I mentioned before, you just come here. You can copy this table, copy as a table, copy as this as a picture, take it to where you want to play it around with, remove what you don't want and make it look nice, depending on what you want to keep and what you want to leave. There are, of course, commands in Stata where you can actually go and put a command and it brings in that APA format of presenting results without necessarily going to do the hassle of these other issues that we have to. One thing Dr. Kochefos for used the Stata before. One thing which I just mentioned, I want to mention, which is important. Now, once you have worked through your work like this, you can save these commands, all of them, copy them, save them. Next time you just run. You don't have to type or do whatever. Even if you stay 10 years later with the same data set, you just come and run. What you only have to eliminate are those red commands. I can even delete it from here. I don't need it because that was a mistake and it will not run. So we can even remove it. So Stata has something called a do file. To check. So once you've finished running all these things, you can save your commands. Just copy, select all, copy them. You can even take them into Word and keep them somewhere. I think I had tried to do this, but that means I first have to stop and sharing. So you can keep these commands in simple terms. What I'm trying to explain is you can save these commands in what Stata calls a do file, and even add notes in that do file. And then you can run afterwards, repeat without retyping all these things and play the results again and make adjustments where you need to. And so, but these are, interface specific issues which you can learn with time for what we have. Okay.
Okay, thank you, Bernard. I don't know whether there is any comment in view of the presentation.
Okay. So I hope people can take this. This is just another approach to research, like I think Dr. Olugembe mentioned 2 weeks ago. Has nothing to do with economics. Anyone can analyze their works using the panel data, and you sit down, construct your own panel, depending on the variables you have, depending on your research questions, and then you go through these steps to make your write-up for publication or for whatever.
Okay, thank you. Dr. Gideon, I don't know whether they are in. There is some issue we are trying to say and really wanted benefit from. I don't know whether you can even recall it. I think Gideon is not in, Dr. Gideon. Okay, maybe the other thing I remember I had a discussion with you. Some of the people called me and they felt that the unique aspect about Stata is the issue of issuing commands. But some people may be interested in having the interface. Maybe take us briefly through the interface, briefly.
Okay.
Yeah, briefly.
So file, just like any other program, I guess, especially if you're familiar with the SPSS, what file does elsewhere is what file does in Stata really. Open, save, view. There are a few of these things which just come in. When you see log, it means you can keep track of these things, and actually which I should have done, so that at the end of this, I would have carried this whole results table into Word as one document. You can import data from other spreadsheets or other programs, including SAS, for those who have used the SAS before. But you can also export as data back to other spreadsheets, depending on what you want to do, and then print, and these recent files you have opened. Edit, again, copy paste. We always right click on Windows when we are editing things. So find next table copy option is if you are copying a table to tell you remove or vertical bars or lines if you want them on. So area possible is the data. This is a wide issue which has both data management, editing data if you have to change or enter some variables, describe data, try to understand it. You can list variables, you can inspect, you also can run summary statistics depending on what you want to report. But this data area is largely about characteristics. Now, combined data sets, you can have one data set as one file and another data set as another file with the same variables, and you want to combine the two data files together. So you can do that in Stata. Sometimes you can also append data sets. Appending meaning I have stopped on observation number 10. Now I have observation 11 to 20. So I just bring that file which has 11 to 20 and just append to the first one. And that's what appending does here. So this section is really for data management related issues. I want to manage my variables, rename, label, all those things which we did. You can also create new variables I want to create an interaction variable. For instance, I'll say generate female educ, which will be interacting female and education as a new variable. So now here I have a new variable called female edu, which I can also label label variable called fem educ, which is interaction So now I have a new variable. I can look at it and see how it looks like. We didn't have this before. Now I have a new variable which says gender and education for that particular case. So go ahead and you can go ahead and also manipulate data. Stata is also can be used as a calculator, by the way, just like we do in Excel and other spreadsheets. You just, if I want to add the two figures, the only command is display. When you put the word display before anything, then you are telling it to do any computational work. So for instance, 45 times 6. Then it can tell you the figure here, even if it is a fraction, is I want to display maybe 1/3 plus maybe 4/5. Just also compute it for you for whatever case. So any this you can use it like we use for any other thing as we do. Graphics really to do with things we always displaying in our research works. A very rich set of on what you know. If you go for distributional plots alone, so many things we can also plot, and we are used to bar charts and dot charts and pie charts and histograms, contour plots, and managing graphs, including naming and all those things. There are time series graphs, parallelogram, running time series, panel data, all those things to do. The statistics, which is the most extensive menu here, is where we go for everything. Remember, you come here after you have specified in your methodology what you are running. And like I mentioned before, what determines your choice of n of this estimation is your dependent variable or outcome variable. Like I showed you before, there is even in SEM that you can start building your things are variable. They are an add observed variable. You can draw all those things that you can also make in other things. Of course, this is things to choose for whatever. So people who are familiar with SEM, you can still bring your data here and analyze here for reference. So so it is really what ordinal outcomes. All these estimation approaches and math models, depending on what you're analyzing. Treatment effects for people who are in evaluation issues, non-parametric estimations that we always talk about, the bootstraps and etc. So yes, for results, this which I've told you about. It also has a very beautiful help. I mean, just anything, if you say help correlation, if you just type here help correlation, and it should be you should open, I don't know, maybe because I'm sharing, yes, you should open your window here, which has come, and you don't know about, so it brings you a topic, so chapters on correlation. Then you come here and see if I want correlation, then it tells you to look for different options of, correlation estimation as well, how I should, including their commands. If you are not sure about anything, it has a very big menu for whatever you can find the meaning of some of these things once you are having them. So Dr. Kochi, that's it. I think people who are on this call are using different any other thing. It's just sitting down if you're interested, and then you walk through and you can learn or teach some of your things yourself. Okay. Dr. Kochi has the internet issue, so that's why possibly he's off. Friends, if there are no questions,
thank you, Doctor, so much for your presentation. I've noticed as a student, we may go through the following scenario. You may know the data you want, and you may collect it from UBOS to perform a panel data analysis. Can you take us through your Excel? And because I've noticed your Excel is advanced and the way you've prepared your data according to those columns. And then further, if I've got my data, how do I actually bring it into to Starter, like the way you have done your presentation? Thank you so much, Doctor.
All right, let me get back to Zoom. Okay, let me see if I can see as the file that I used. Okay, Jerome, I hope you can see my screen.
Yes, now, thank you so much, Doctor.
Honestly, panel data usually is your own construction. The first thing is to populate your columns with variables. Y1, X1, all things according to your conceptual framework. So going to UBOS actually should have this kind of framework. Your variables are clearly defined in your columns. So you'll ask UBOS for two things. I am studying households or districts. Then you'll have all your districts populated in these rows. Once you're done with the rows, then you'll ask UBOS for one thing, the time dimension. I mean it, Dr. Which is calling. Yes, doctor. Okay. So you'll ask time. I'm studying from 2003. I would wish you, but you give me data from 2003, maybe up to 2010. And then you'll have the first district here. Maybe it is Lira. Then that is the first sub panel. Okay, so you'll enter figures or variables or data from UBOS on all your variables here, which you have listed. Once you're done, you'll ask the UBOS and say, I want to add now ginger. Ginger, they also give you, you say my next district is ginger, then you sit down and also start from 2000 2003, this is what you'll ask UBOS, how it is already existing in their documents. For your job is to sit down and extract all that information. So you'll do this, constructing these things yourself from individual number one or enterprise number one. Here I'm talking about the districts. Now I finish. Then for all the years which you want, you also do. And then you do the same thing for all until you're done. Most of this data will exist in somewhere, so it is your job to look for the values or information and keep populating here up to the last individual that you have. And once you're done, that is your panel data. Yeah, these sub panels, when you combine them, the sub panels is lira and yin and any other thing, then you're done. That's why the data which you was using is also based on the same approach. So these were individuals or workers who were observed each for 7 years. So we first finished with the first person for the same period. I'll just put space here. Then you come and the video 2 or populating the video 2 again for the same period of time, the same variables. Then once you're done, and that is your panel. Then you can take it to starter, depending once you filled everything, there are no gaps, you're ready, you're comfortable with what you have done. So then the first issue is you open your starter. I'll clear this because you can't bring in another data set when there is already another data set. So clearing here means I will now removed all of the data which you have been running on. Once I'm convinced this is done, then of course you have to close that file. If it is open, it may not allow you to bring it. So you go to file. I want to bring that data. I know I told you have to save it as delimited CSV, and then you browse, you look for that file wherever you have saved it. Mine is there. You open it, just use for where you are.
Sorry, doctor. Your screen is not sharing.
Oh, forgot to do that. Sorry. Should have. Okay. Share. Where is my data? Okay. Let me close this. So you open your starter, this is where it is, and that is it. So once that is done, you'll come to file. You want to import just like you do for most of these other programs. You must have saved your Excel file as a CSV for starter to directly read it and bring it. So I click on this, and then it will bring this box, and then it tell you to browse, just like we look for files everywhere. I have saved mine here as with this file name. That's why it must have after the dot must CSV. So that is select it, and then you open. It previews for you to just be sure am I bringing the right file which I worked on, and if you're okay with it, you close off, and here your variables are here. So if you have saved your command mentioned to you before, the do file which I mentioned, do file things which are already written here. I should have opened. I can't open the two things on Zoom at the same time. Okay, but the simple process really is the same story you are doing elsewhere with the other software is the same thing you can do here. Yeah. I have any issues? Oh, Kasozi, if the same. I see Kasozi asking, if the same data set applied with Stata was used basing on other packages, different results would come out. What is your comment? Yes, these softwares, each of them are built with some precision. If you run a regression in Excel, in SPSS, in Stata or in other software, you cannot exactly get the same score of coefficients. There will be variations with some precision of magnitude. Now, those are software issues beyond you. So some people have 0.014, some people have 0.023, but it should rotate around the same magnitude. Yes, different softwares will give you a little bit different coefficients or figures with the same data set. And that's why people keep pushing and developing for these things. So you cannot say, I use the SPSS, mine is different, but shouldn't be very significantly different. But yes, you'll get a little bit different scores, and those are software differences that comes with for using different places. All right, Dr. Okochi, I think he's not on. I'll take this to Professor Anta if he's here for conclusion of today.
Okay, thank you. Thank you very much, Bernard, for the great job that you've done. I'm sure everyone present on this platform is appreciative of the great job. I want to thank my senior colleagues who are here, Professor Twaha Kawase. You are welcome, Dr. Wilfred Kokas, Goretti, Charles, Dr. Ahmad, and the rest. Thank you very much for being with us. Next week, we shall have Lola, Professor Lola Orobia, taking us through interpreting and presenting data, right? Presenting data and interpreting results. I've already sent a message on your platform. And very soon we shall be having also Professor Twaha Kawase talking to us. Maybe I'll give him a minute, actually 2 minutes, to talk to us and also close the session. Professor Twaha Kawase, over to you.
Okay. Good morning, everybody. Thank you, Professor Antai, and thank you, Dr. Godwin. I've came in late, but I've been able to catch the tail end, and I appreciate the presentation. And thank you very much for the initiative. Learning never ends. You keep on learning and learning and relearning and learning and relearning. That's why creation of knowledge keeps on evolving. So thank you so much. I look forward to the next presentation. And good morning, everybody.
Have a nice morning, nice Sunday. Bye.
Bye.
Bye-bye.
Bye.